Assalamu alaikum. Hello everyone. We start our next topic, complements. In general, in any numbering system, there are two types of complements. R dimension or R minus 1's complement and R's complement. So in decimal here we say nines and binary ones, for example, in octal sevens, etc. And for the R's complement, decimal we say tens complement in binary twos and eights in octal. Next, what is R minus 1's complement and what's R's complement? We have a number n in base R numbering system with n digits, with n digits. Then R minus 1's complement of the number n equals to R to the power n minus the number n minus 1. Or we can write it as R to the power n minus 1 minus n. While R's complement of the number n equals to R to the power n minus the number n. So this is the definition. From the definition, you can see that R minus 1's complement is less than R's complement by 1. Or if we add 1 to R minus 1's complement of the number n, we obtain the R's complement of n. So R's complement of the number n equals to R minus 1's complement of the number n plus 1. This is true for any numbering system. Next we move to examples how to find R's complement and R minus 1's complement. We start with R minus 1's complement. How to find? Suppose the number n equals to 25. Then n small equals to 2, since we have 2 digits. 9's complement, because we are and decimal r equal 10. 9's complement r minus 1's complement of 25 equals to r10 to the power 2 minus 1 minus the number in 25. This is equal 9, 100 minus 1 minus 25. And the result is 4, 7. $74 is the 9's complement of 25. Note that 10 to the power 2 minus 1 is 9. 10 to the power 3 minus 1 also produces 3 9's. 10 to the power say C minus 1 produces C 9's. This is valid for any numbering system. For example, in any base R numbering system, R to the power n minus 1 produces the larger digit in the R numbering system is R minus 1. R minus 1, R minus 1, etc. R minus 1 digits, and the number of these digits is n. For example, in binary, 2 to the power 3 minus 1 is 3 ones. And 2 to the power 4 minus 1 is 4 ones. 2 to the power 5 minus 1 is 5 ones. And in any numbering system, you can note that. We go back to our example. So instead of computing R minus 1's complement in this manner, we could subtract all the digits in the number from R minus 1, or in decimal from 9. For example, 2, 5. To find its 9 complement, we subtract all digits from 9 directly. 4, 7. And to find, for example, the 9th complement of the number 8, 3, 4, 9th complement, we directly subtract from 9. 5, 6, 1. This is the 9th complement from 8, 3, 4. In binary, if we need to find 1's complement of the number 10 1, 1, for example. And it's required to find 1's complement. This is number n, small n equals number of digits 4. So 1's complement of n equals 2 to the power 4 minus 1 minus the number 1, 0, 1, 1. We already know that 2 to the power 4 minus 1 is 4 ones minus 1, 0, 1, 1. If you subtract 1, 1, 1, 1 minus 1, 0, 1, 1, 1 minus 1, 0, 1 minus 1, 0, 1 minus 0, 1, 1 minus 1, 0. So this is the 1's complement of this number. Really, the number is 11 and this is 4, so the total is 15, which is the maximum number that we can represent using 4 digits. Here we have another observation. Subtracting any bit from 1 means that we reverse its state. If it's 1, the result becomes 0. If it's 0, the result is 1. So we can directly apply this rule to any binary number. 1, 0, 1, 1, just convert the state. 1 to 0, 1 to 0, 0 to 1, and this is the 1's complement directly. For example, to find the 1's complement, the number n, 1, 1, 0, 1, 1, 0, 0, 1, in binary, then the 1's complement is equal to directly 0, 0, 1, 0, 0, 1, 1, 0. Also, this is 1's complement. In any numbering system, you can use the same rule. For example, if we have the number r equal 8 and the number n in octet equals 2, 3, 4, 5. We can apply the formula. I'll leave as an exercise for you, but we can directly write here the 7th complement, this number, by subtracting all the digits from the highest digit in the octal numbering system, which is 7. 7 minus 5, 2, 3, 4. Next, examples how to find 2's complement or r's complement. Again, in decimal, if we have the number in decimal, if we have n equals to, again, 25, small n number of digits equal 3, 10's complement of this number, 10's complement of n is equal to 10 to the power, n equal here 2, not 3, 2. 10 to the power 2 minus just the number 25, which is 100 minus 25, which is equal 75. In the last screen, we found out that the ninth complement of 25 is 74. If you add 1 to 74, then you get 75. We have, for example, another example. We have the number n decimal are equal 10 and the number n is equal to 250. Then n small equal 3. Then the 10th complement of the number n equals to 10 to the power 3 minus this number, which is equal to 6. You can exercise by yourself and find out that the ninth complement of 250 is 749. The 10th complement is 7. There is a quick rule here. A quick rule. In any numbering system, leave the zeros as they are. Subtract the first non-zero digit from R and all the remaining digits from R minus 1. For example, if we have the number 3, 5, 6, 0, 0. Its 10th complement directly is equal to 0, 0. We subtract the first non-zero digits from 10, which is 4, and the others from 9, which is also 4, 6. In binary, we use the same rules. For example, they have the number n equals to 1, 0, 1, 1, r equal to binary, number of digits n equal 4. So 2's complement of the number n equals to r, which is 2, minus to the power n 4 minus the number 1, 0, 1, 1, which is equal to the power 4, 1 with 4 zeros, minus 1, 0, 1, 1. Before going to any quick rules, let's do the subtraction. 1 with 4 zeros, 1, 1, 0, 1, 0. Although arithmetic operations in binary are easy to know, 1 plus 1 equals to 0, carry 1. The others, 0 plus 0 or 0 equals 0, 0 plus 1 or 1 plus 0 equals 1. But if we subtract 0 minus 0 or 1 minus 0, 1 minus 1, here 0, 1, 1 minus 1, 0. But if we subtract 0 minus 1, like in decimal, this is 0 minus 1 equals 2. We have to borrow. Here we have, it will become 1 0 minus 1 1. So 0 minus 1 1. But with, remember, with a borrow. With a borrow. With a borrow. Very quickly. 1 minus 0, we need to borrow. We need to borrow, we need to borrow. Here becomes 0. And this becomes 1 0, 2. If we borrow, it becomes 1. Again here 1 0. We borrow 1, it becomes 1. 1 0. If we borrow 1, it becomes 1. And here 1 0. 1 0 minus 1 1. 1 minus 1 0. 1 minus 0 1. 1 minus 1 0 0. So the 2's complement of this number is equal to 0 1 0 1. And really the complement of 11 to 16 is 5. Is 5. We can use the quick rules here. Either we can obtain the 1's complement directly, 1 0 1 1, and the 1's complement by reversing 1 to 0 and 0 to 1. This is the 1's complement, and add to it 1. So this is the same result. Or we can subtract the first non-zero digit from R or from 2 and all the remaining bits from R minus 1. Why do we need complements? So far we are familiar with 2 types of complements, R minus 1's and R's complement, and we know how to find R minus 1's complement and R's complement of any number in any numbering system. Usually computers perform subtraction using addition with complement. Now we will start with subtraction using R minus 1's complement. And then we move to R's complement. Suppose we have the number A and B, and we need to subtract B from A. We follow the steps. First, we find R minus 1's complement of the number B. Next, this is the first step. The second step, add the result in A in step 1. In step 1 to A. Third step, we have a sum here. After step 2, we inspect, inspect the sum for an end around carry for a carry from the last stage. If yes, if there is a carry, there is an end around carry, add it at the end around carry to the least significant digit of the result, the sum. If no, if there is no end around carry, then the result is negative and represented in the complement form. Complement form. These are the steps to perform subtraction using addition with R minus 1's complement. Now examples. Again, we have the operation A minus B. We find the complement of B, add the result. As if it becomes as if we are adding A to the complement of B. Now, if there is a carry after the sum, then we add it to the least significant bit. Otherwise, the result is negative. For example, we have in decimal the two numbers 7, 4, 5 minus 5, 4, 3 are equal 10. We find first ninth complement of this number, ninth. And we know how to find it. We subtract all digits from 9. 6, 5, 4. Now we add with A. Add 6 plus 5, 11. 5 plus 4 plus 1, 0, they carry 1. 1 plus 4, 5, plus 7, 12. 2 with a carry 1. Here we have end around carry. End around carry. So we add this end around carry 1 to the least significant digit. The result is 2, 0, 2. It's correct. In binary, the same thing, or in any numbering system. For example, if we have two numbers 1, 1, 0, 0, 1, 0 minus 1, 0, 0, 1, 1, 1. First, we obtain the ones complement 0, 0, 0, 1, 1, 0. Then we add this to A. 1, 1, 0, 0, 1, 0. 0, 1, 0, 1, 1 plus 1, 0. They carry 1, 1 plus 1, 0. And we have end around carry 1. We should add it to the least significant digit here, plus our final result will be 1, 1, 0, 1, 0, 0. This is our result. You can check by converting these values to decimal and the result to decimal. Let's take more examples. If the result is negative, for example, we have in decimal r equal 10 again, and we have the number 2, 4, 5. We need to subtract it from 7, 3, 2. We find the 9th complement by subtracting all digits from 9, 7, 6, 2. We add to A, 2, 4, 5. You see, we do not perform any subtraction, we perform addition, but with complement. 12, 10, 11, 5. And the round carry equals to 0. The result is negative. And in complement form, minus the 9th complement of this number is 7, 8, 4. This is the result. Please check it. Later on, we will speak about the minus sign because computers do not perform operation in such manner. Example on binary, same. If we have two numbers, for example, 1, 0, 0, 1, I'll take this, minus 1, 1, 1, 0. This is 9 and this is 40. We take 1's complement of this number, which is equal to 1, 0, 0, 0. We add it with this number, 1, 0, 0, 1, 0, would carry 1, 1, 0, 1. The inter-round carry is equal to 0. So our result is negative. And represented in the complement form, in the 1's complement form, which is 1, 0, 1, 0. Really, minus 5. This is minus 5. Minus 5. If the first number is greater than the second number, there will be a carry. So if we have 1, 1, 0 minus 1, 0, 0, vice versa, it's 14 minus 9. We complement this value, 0, 1, 1, 0, add A to it. This is the complement, and this is the first number. We add them together, 0 would carry 1, 1 would carry 1, 1 with 1, 0, and we have here an end around carry. We should add the end around carry here, and we have 1 0 1 0 5. So this is subtraction using r minus 1's complement. Now, steps for subtraction using r complements. Subtraction using r's complement. We have a minus b. We again find r's complement, b, add the result in step 1. In step 1 to a, inspect the result, examine the addition, sum, inspect the sum for an end around carry. Yes, there is an end around carry, just ignore it. Here we save one step. We do in the r minus 1's complement, we have to add the end around carry to the least significant digit to obtain the correct result. But here we do not need to do that. So this is one advantage of using r's complement over r minus 1's complement. If no end around carry, no, then the result is negative. And represented in the complement in the r's complement form. In the r's complement form. Again, the steps. We are performing subtraction, a minus b. We find the r's complement of b, add the result to a, inspect the sum for an end around carry. There is an end around carry. In the r's complement, we ignore it. If there is no end around carry, then the result is negative and represented in the r's complement form. Examples. Suppose r equal 10 and we are subtracting 7, 3, 5, minus 2, 1, 7. So we have to find the 9th complement, the 10th complement, the 10th complement of this number. We subtract the first digit from 10, 3, all the remaining from 9, 8, and 7. We add with 8, 7, 3, 5. 3 plus 5, 8, 11, and 5, there is an in the round carry, 1. We just ignore it. This is our result. Please check it if it's correct or not. We do not need to add it as in the r minus 1's complement. Again, if the result is negative, for example, if we have 2, 3, 5 minus 8, 1, 7, we find the tens complement of this by subtracting the first digit from 10, 3, and all the remaining from 9, 8, 1. We add to this number 3, 2, 3, 5, 8, 11, 4. No in the round carry. Since there is no an in the round carry, our result is negative and represented in the tens complement form. The tens complement form, this number is 2, all the remaining from 9, 8, and from 9, 5. This is in binary the same. We do the same. For example, if we have the number 1, 1, 0, 1 minus 1, 0, 0, 0. We find the 2's complement, this number, you see, 0, 0, 0, and the first digit, non-zero digit remains as it is. We add with this number 1, 1, 0, 1, 1, 0, 1, 0, and there is a carry 1, we just ignore it, and this is our result. Really, you can check, this is 13 minus 8, and the result is 5. Everything is okay. I'll take another example. If the number is, the result is negative. For example, we are subtracting 1, 0, 0, 0, minus 1, 1, vice versa, 0, 8, minus 30. The 2's complement of this number, the first non-zero digit as it is, the others we complement them, we add to 8. 1, 1, 0, 1. The end around carry is equals to 0. Therefore, the result is negative and represented in the 2's complement form. This is 1, 0, 1, 0. This is minus 5. Most computers use 2's complement form to perform subtraction through addition, and they use 2's complement form to represent negative number, and we'll speak about that more in the next lectures. So we are done with complements. In next video we are going to speak more about minus sign and different forms of representing numbers, and we are going to repeat these examples but when the sign is there. For now, thank you.